Have you ever wondered why the Challenger disaster happened? Or why Tesla truck demonstration failed, if you guys watched it, when the glass shattered? Or why Titanic actually sank? So all these disasters and observations can be understood with the knowledge of materials. In this chapter, we're going to address the following issues. What is material science and engineering? Why are materials important? Why is it important for us, the engineers, to understand materials? Materials engineering is the core of all engineering practices. All engineers need to learn and understand the behavior of materials and, of course, the underlying reasons behind it. Materials are the primary building blocks for all engineering developments, and technological advancements are achieved by the development of materials. So what is material science and engineering? Material science involves investigating the relationship between the structure and the properties of materials. Because if we understand the science behind it, science behind why the behavior of materials are observed in a certain way, you can actually easily design and develop new materials with new properties. This is material science. And materials engineering involves the design and engineering of a material to produce the desired properties, of course, using the knowledge of science behind it. So why materials are important? Of course, if you look around yourself, you're going to see what would it be like without all these materials that exist in our everyday world, like the cell phones, airplanes, television. Actually, the development and advancement of society is directly related to their capability to produce materials. In fact, early civilizations have been named after the materials which were available and used as tools: Stone Age, Bronze Age, and Iron Age. So what is today's materials age? Is it silicon age, nanomaterials age, or polymer age? So all these materials are currently shaping our society, making our existence comfortable. Sophisticated electronic devices are made from silicon-based semiconducting materials, like the iPhones we have. Polymers, they are lightweight, cheap, and very easy to manufacture. And we use them everywhere nowadays, from toys to synthetic heart valves. Next age of humanity might be labeled as nano age, because we are observing that nanomaterials and nanotechnology is being demonstrated to be very useful in healthcare and energy storage. Because at nanoscale, materials show incredible and unique properties. So why study material science and engineering? Because things engineers design, they are made of materials like products, devices, components. And now we are requiring new materials with new properties to fit our designs. And effective design and usage of materials can be achieved by fully understanding the principles of material science and engineering. So actually, material science and engineering can be defined as the relationship among the structure, properties, and processing. Okay, so there is this connection among the common elements in material science and engineering. So if you look at properties, they depend on the structure. And properties determined by processing. And processing, of course, affects the structure. So all the useful properties of materials, they are strongly depending on the internal structure of the material, and the internal structure depends on how the material was manufactured. So in this example, we are going to see this relationship between the properties, structure, and processing. So processing parameters such as cooling rate, that means how fast you cool down the material. And in this example, it is steel. Our material is steel. So how fast we cool the material will directly affect the resulting structure of material, as you can see. And the structure here shown, demonstrated by the microscopic images given, A, B, C, D, right? And this is the same material, but it is showing different structure, right? And why this is happening? Because they are cooled down at different rates. As you can see on the x-axis, right, the processing parameters are being changed. So as we go towards this direction, 1000 degrees C per second, we are increasing the cooling rate of the material. And the cooling rate, as it increases, the material exhibits, as we see under microscope, right, more finer structure. And of course, this type of structure will directly determine the property of that material. In this case, the property is a mechanical property called hardness. And as we can see that as cooling rate increases, the hardness increases, because the structure of the same material basically is changing still. So this is just a demonstration to you guys to understand the relationship between properties, structure, and processing. Let's look at the classifications of materials. 3 basic categories: metals, ceramics, and polymers. Why? Because all these material families have common atomic structures. Of course, in addition to that classification, there are composite materials, which are basically engineered combinations of 2 or more different materials. So what are metals? Metals are basically composed of metallic elements. Examples: iron, right? Aluminum, copper, nickel. And they also contain non-metallic elements, such as you can add in small amounts, you can add carbon or nitrogen to iron, which will give us steel, right? So we can add small amounts of those non-metallic elements to the metallic elements and giving us metallic alloys basically. These materials are very strong, ductile. Ductile means, we're gonna see, but ductile means easy to deform. Okay, the material can be deformed to a large extent without failing. And they also have high electrical and thermal conductivities. They are not transparent to visible light. The bad thing about metals, they are susceptible to corrosion. And all these properties are because of its atomic structure. So you need to guys understand this relationship. So the metallic materials, they have non-localized electrons, meaning the electron is not bound to a particular atom and it is free in the structure, freely floating in the structure. Therefore, this gives them a high electrical and thermal conductivity, and also gives them not being transparent to visible light. because the electrons scatter the light, and usually this gives metals a shiny appearance. So polymers or plastics, they are organic molecules. They are organic molecules just like our bodies. So they are made up of carbon, hydrogen, and other non-metallic elements such as silicon and nitrogen. And some examples in my mind is polyethylene, right? Abbreviation polyethylene. Usually the abbreviations are used for polymers because they have long names. Polycarbonate. These materials have low densities. They are not strong but ductile, meaning they can easily be formed into complex shapes. They are good electrical and thermal insulators. Okay, so that means they are not conducting electricity and thermal energy. Okay, so they often, the bad thing about plastics, they soften or decompose at very modest temperatures. So which limits their use. Because they are lightweight, they can be used in many applications, but this is limited by their thermal properties. Basically, at very low temperatures, they just decompose or soften. Everyday examples are milk bottles, food packaging, drinking bottles, right? These are all polymers. And everyday plastics around us are recognized by numbers that are labeled on them. If you just pick up a water bottle right now and take a look at the bottom of it, you will see a number. And that number will tell you what type of polymer it is and how you can recycle it. I provided you guys a link for you to read in Canvas. Please take a look at it. So ceramics, what are they? They are compounds between metallic and non-metallic elements. So compound, right? Compound means metallic and non-metallic element comes together at certain ratios. Okay, and these are usually oxides, nitrides, and carbides, such as alumina or aluminum oxide. 2 aluminum, 3 oxygen, right? Alumina or aluminum oxide, same. Silica or silicon oxide. This is not correct. Let me correct this. Right? And then this is an oxide example. What about carbide? Silicon carbide and silicon nitride. Also glass. Those are ceramics. Ceramics are very strong materials. It is because of the covalent bonding they have. They are very strong materials, especially under compressive stresses. But the bad thing about ceramics, they are very brittle and they have low thermal and electrical conductivities, but they are resistant to very high temperatures and harsh environments. So all engineers, they need to select materials for their design, and currently there are 160,000 materials available to us. So how then engineers will select their material for their design? First, we need to determine the required properties for that application, right? And properties such as mechanical, electrical, thermal, etc. And of course, many times, not only mechanical properties will be required. Together with mechanical, there might be the requirement of an electrical property. So, combination of properties. And after that, we're gonna rank materials based on these properties and identify the candidates. Okay, identify the candidates. And based on that, we can choose the best material based on the properties that we rank them by, and we can choose the best material. And of course, therefore, the corresponding processing technique can be determined based on what size and shape you want, what set of properties you want, such processing technique examples, casting, welding, etc. Okay, so material selection by itself is a big topic and covered in a class that I'm teaching called material selection. And let me give you a little advertisement here. In that class, we are learning a systematic approach developed by Professor Ashby from Cambridge University, and we have a software available. We are doing the material selection using this software called CES Selector, which is located in the CAD lab. And your book mentions about this approach and the software, and it is also beneficial for you guys. And if you're interested, you can contact me or go to the CAD lab and discover the software yourself. So when we say a property of a material, what do we mean, right? So properties of materials, they fall into 6 categories: mechanical, electrical, thermal, magnetic, optical, deteriorative. So mechanical properties, of course, related to the deformation when a force is applied. And examples to mechanical properties are hardness, strength, stiffness, or resistance to fracture. Of course, this is directly related to the structure of the material. We just have learned that the properties are related to the structure, and in this example we are being demonstrated by this concept. Here we see how the hardness of a common steel is changed by increasing the carbon content. So by adding carbon into iron, this is steel, right? So the steel structure, as we add the carbon, basically the hardness of the steel is increasing. Okay, so how we can manipulate basically a mechanical property by changing the structure. Electrical conductivity, electrical properties. So electrical properties relate to how material behaves when an electric field is applied, right? So electrical conductivity, of course, a property again that can be changed by changing the structure. And here is an example how the resistivity of copper is affected. And we know copper is a very good conductor, right? So resistivity here and temperature on the x-axis. We are seeing it for the pure copper, that as we increase the temperature, the resistivity, electrical resistivity is increasing. That means the conductivity is decreased, right? We can expect this behavior because as we increase the temperature, atoms will start to vibrate, and this will impede the electron motion pretty much. And as we increase, in addition to that, there are other ways. If we increase the impurity content, in this case, the impurity is the nickel alloy. As we increase the impurity content here, the nickel is added a certain amount to the copper. We are seeing that actually, right, compared to the pure copper here, we are seeing that resistivity for a certain temperature, the resistivity increased. That means conductivity decreased. Again, this is the same concept because the nickel atoms are obstacles to the electron motion. Therefore, it is increasing the electrical resistivity. And in addition to that, also deforming the material. So we just deform the same material here. Okay, so the same, but now we deformed it. Of course, deformation again increasing the resistivity because you are disrupting pretty much the crystal structure and creating obstacles to the electron flow. So Thermal properties. Thermal properties, they are related to behavioral changes of material with temperature. And some examples of thermal properties: thermal conductivity, thermal expansion, thermal shock resistance. For example, thermal conductivity, it is the material's ability to conduct heat. This is also affected by the structure. In this case, we are seeing that we know the copper is a good conductor of heat, and if I add zinc into it, right, as I increase the amount of zinc addition into copper, it decreases. So it will start here for the pure copper's conductivity, but as we keep adding zinc, it is decreasing the thermal conductivity of copper. Again, this is due to electrons being scattered by impurities, zinc impurities. So highly porous materials are poor conductors of heat because there is air in the structure, basically, right? And an example is that the materials used in space shuttle thermal protection systems, they are made up of silica tiles, but approximately 90% is air, and the rest is silica from sand, and air is a poor conductor, and therefore this is providing us a material that has a very low thermal conductivity. In fact, it is demonstrated here. Basically, this is the microscopic image. We are seeing how porous the structure is and how low thermal conductivity it has, because the guide is able to hold the material without getting burned. Magnetic properties are basically responses of the materials to the application of magnetic field. And magnetic storage is where such properties are utilized. In this illustration, we are seeing a material which is used as a recording medium, a magnetic material. And we see this material is capable of being magnetized, basically, by the application of the magnetic field here. Okay, it is being magnetized and acting as a storing this magnetic energy, basically. Okay, so magnetic permeability here is the material's ability to magnetize under applied magnetic field. And again, this property is affected by the structure. In this case, it is affected by addition of elements such as silicon to the iron structure. And we know iron is a magnetic material, and addition of the silicon, let's see how it changes. So we are seeing with the application with the magnetic field how the material is magnetized, and this is defined as the magnetic permeability. And as you can see, it is increasing with the addition of silicon. So you can see it is we are able to create a better medium for magnetic storage. Light transmittance of materials depends on their structure, of course. And in this case, we're going to see an example where we are observing that optical properties are controlled by grain structure, and we're going to see what grain structure means. So aluminum oxide may be transparent, translucent, or opaque depending on the material structure. You guys need to be careful. This we are talking about the same structure, same material, right? This is alumina or aluminum oxide, same material showing different properties. The only thing that changes is the structure. Okay. In the first case, we are seeing a single crystal. So single crystal means, let me try to explain it to you. So if you look at under microscope, let's see, okay, what we are seeing for a single crystal is the atoms are aligned in a certain order. Okay, so all atoms, and so they are aligned on a certain direction. Okay, like this. So this creates a property which we called transparent. materials, right? Transparency. And what if the atoms within the material is actually, they are not all aligned in a certain direction? What if they align in randomly in different directions? That's what we create polycrystalline material. So small grains, it says. So let's look at under microscope. We have grains, different regions. They are called grains, and all the atoms within those grains have the certain align in a certain direction. But when we compare the grains to each other, atoms have different directions. Okay, they are aligned in different directions, like this. Okay, so this creates an optical property we call translucent. Okay, so as you can see, this is not single crystal. This is a polycrystalline material, meaning many crystals inside, many small grains. And in addition to that, if the material has porosity, like we are seeing in this example, the material is optically opaque. Okay. So the deteriorative properties, what are these? These are related to chemical reactivity of materials such as corrosion. And corrosion, you can guys think about it like it is, the environment is like eating up your material, and you are losing material to the environment, and therefore cracks can form. In this case, we are seeing a steel bar which was immersed in seawater, and of course it is under stresses. Okay, it is under stress, right? And then this will combination of the environment and the stress causing cracks to form. One way to prevent this is do heat treatment, because heat treatment is able to relieve the stresses inside the material. And we are seeing this is for aluminum alloy. Okay, for the same type of loading here, crack growth rate can decrease if we heat treat the material. Okay, basically put it in an environment where we apply heat. Okay, it is because it is relieving the stresses inside and lowering the chances of crack formation, basically. So let's finish this chapter by an example of material selection. So how to select a material for artificial hip replacement. And in this figure, we are seeing the anatomy of a human hip joint and adjacent skeletal features. The human hip joint occurs at the junction between the pelvis and the upper leg bone, right? This part. And of course, the damage to this region can be very painful and reduces the range of motion. Therefore, the question is now here, what type of properties would it be necessary for such material? The first thing is biocompatibility. So that means that the material has to be compatible with the human tissue, not toxic, and it should not be reactive to body fluids. It should be corrosion resistant, right? Besides, it should support mechanical forces. It should have a good mechanical strength and a good lubricity and high wear resistance, right? So, of course, this hip replacement has multiple parts, as we see here, and stem which is inserted to the hip bone here. Okay, and there is the head which affixed to the stem, and the shell which is attached to the pelvis, and the liner into which the head fits. All will require different properties, of course, and slightly different. Currently, these materials are being used. Titanium alloys, they are preferred for stems, or the cobalt, chromium, molybdenum alloy. Okay, and these materials have excellent mechanical properties and corrosion resistance because frictional forces are generated at the ball. So we need a material that has a high wear resistance, basically. And those are usually again the same alloy and ceramic materials. And shells are made up of again the same material as the stem, titanium alloys. And liners can be a polymer or a ceramic. And polymers have, of course, excellent wear and oxidation resistance, which make them suitable for this application. And here we see after the material is implanted. So in summary, what have we learned? We learned that as engineer, we need to understand the relationship between basically structure, properties, and processing, right? So we can make a correct decision. And we have learned that materials are classified as metals, ceramic, and polymers. And we have different properties: mechanical, electrical, thermal, etc. And as engineers, we have this important role to select the best material for our design, for the application.